Hey everyone, it's Ken. In this video I want to show you how to prove the fundamental theorem of calculus part 1. And what this does is it tells us, say we've got a function and we want to take the definite integral from a to b. If we know an antiderivative for that function, then actually we can use that antiderivative to quickly calculate the definite integral of the function. So let's see how to set it up. So you're starting with a function f of x, and say that you know an antiderivative, call it maybe capital F, f prime of x. And you know that's going to be equal to f. And then fundamental theorem of calculus says that if you want to calculate the definite integral from a to b of f of x dx, then you can do this by just looking at your antiderivative and evaluating it on the endpoints. And that's a really nice theorem to have. So for instance, like say you wanted to take the integral from 0 to pi over 4 cosine of x dx. If you just had to use the definition of the integral, limit of Riemann sums, then good luck. But if you've got the fundamental theorem of calculus, you know an antiderivative of cosine is going to be sine. So you can quickly say that this integral is going to be nothing but sine of pi over 4 minus sine of 0. Sine of pi over 4 is root 2 over 2. Sine of 0 is equal to 0. So you can quickly see that the area under the curve of cosine from 0 to pi over 4 is root 2 over 2, which is really nice. So how can we prove this theorem? So what I want to do is I really just want to start with the left-hand side and then show you that it's equal to the right-hand side. And at first, this theorem seems like it might be crazy. It seems like there's no way you could get any traction with it, because what can you do with just f of b minus f of a? Not much, right? But you have to connect this back somehow to the definition of definite integral. And the way we're going to do that, if you think back to what that definition is, the definite integral is a limit of Riemann sums. So it's a limit of approximations to the signed area. And each Riemann sum requires a partition of the interval of a to b. In other words, the partition is just the endpoints of all the subintervals that you want to have. So say that you've picked such a partition, maybe a equals x0, then so on and so forth, all the way up to xn equals b. And here what you've got is f of xn minus f of x0. And so what I want to do to this is I want to do something, this is a technique, you'll hear it referred to as a telescoping series, like telescoping series of numbers. So what I want to do is not just add up f of xn minus f of x0. I want to add up all the other terms in this partition that's given to me. So here's what I'm going to do. Let's take f of x0 and I'll put a minus sign there and add to it f of x1. Maybe I should have written f of x1 minus f of x0, but it's okay. Then I'm going to add to it, let's say, f of x2 minus f of x1. So you see the pattern, x0, x1, then x1, x2. Then I'm going to add up f of x3 minus f of x2. So x0, x1, x1, x2, x3, x2, and so on and so forth, until I get all the way to the end, to f of xn minus f of xn minus 1. And the first thing I want to say to you is that these two sides really are equal. So, and why is that? Because I'm starting here with minus f of a, which is right there. Remember, x0 is equal to a. And then I've got f of x1. But that's going to cancel with the negative f of x1 over here. And then I've got f of x2, but that's going to cancel with the negative f of x2. So everything's going to cancel with the number from the corresponding term, except for f of xn, because that's where I start. F of xn minus 1 will cancel here, but this one doesn't have anything next to cancel with it. But f of xn is equal to f of b. So what I'm left with is f of b minus f of a. So I really didn't change the value of f of b minus f of a. I just included all these other terms in, in this partition that I've picked. And so this is the thing that really lets us go to work. And so what I want to do next is I want to use the mean value theorem on every single one of these terms, every single one of these n terms. And so let's start with the first one, this f of x1 minus f of x0. And I'll actually write this down. So that first term, f of x1 minus f of x0. I'm going to use the mean value theorem on the interval from x0 to x1 applied to the function capital F. So the mean value theorem applies when you've got a differentiable function that's continuous on the interior. Every differentiable function is continuous, so the mean value theorem does apply to this. And mean value theorem says that there must exist a point, call it C1, between x0 and x1, such that this difference is equal to f prime with C1 plugged in times x1 minus x0. But this function is an antiderivative for f of x. So I can rewrite this as f of C1. And x1 minus x0, that's nothing but delta x1. Okay, so if I go rewrite this expression now, applying the mean value theorem to each pair in turn, I'm going to end up with, well, this first one, as I've just shown, becomes f of C1 times delta x1. And when I apply the mean value theorem to this pair, it's going to mean there must exist some point between x1 and x2, let's call it C2, with the property that this difference is now going to be equal to f of C2 times, delta x2. And I'm just going to proceed onward like that. At the very end, I'll end up with some f of Cn times delta xn. And I'll actually come back and write this in summation notation. In summation notation, this is equal to the sum. I goes from 1 to n. I'm just rewriting this expression as f of ci is delta xi. So it's a nice way to write it in like a short, compact way. So to recap what we've done, if you pick any partition, any subdivision of interval from a to b into subintervals, then there will exist points C1, C2, C3 up to Cn inside each one of those subintervals with the property that f of b minus f of a is equal to that sum. So that's pretty cool. And so how do I connect this with the definition of a definite integral? So imagine yourself constructing a sequence of partitions, getting finer and finer and finer. For every one of those sequence, maybe you used right-hand endpoints. So maybe you used xi, maybe you used like delta x equals b minus a over n. And you're just, dividing them up into n equal subdivisions. And then for each partition, you're still going to get that f of b minus f of a, no matter which one you picked, is equal to this, to this sum. But the sum will itself get bigger and bigger and bigger. And so what I would ask you to do then is to think about taking the limit as n goes to infinity of both sides of f of b minus f of a. And then here it's the limit as n goes to infinity of this sum. I goes from 1 to n of f ci delta xi. And I want you to really understand what I mean here. So this, for every n that you pick, for every n, you've picked a partition of the interval from a to b. Could be the right endpoint partition, could be anything else. And then once you've picked that partition, then there exists points ci, such that this is equal to that. And then you're just trying to take the limit of these sums, if they exist. So if the limit does exist, then it will be equal to the definite integral of f of x dx. And that's because that's the definition of the definite integral. If the definite integral exists, then it must be a limit of Riemann sums, and there's a limit of Riemann sums. On the other hand, you've got limit as n goes to infinity of this constant. But this constant doesn't depend on n, so of course it doesn't change as the limit goes to infinity. So what you end up with is nothing but f of b minus f of a equals the definite integral. And so that's the fundamental theorem of calculus part 1. And let's pause and recap what we've done. So what did we have to assume? We had to assume that f had an antiderivative. And we had to assume that f was integrable. So I won't take the time to just write them down on the board, but just remember, for yourself, this proof works when you've got a function that's first of all integrable and second of all has an antiderivative, because those are the two things you even need to write down both sides of this equation. But if those two things are true, then this equation will be true. The thing that links them together is the mean value theorem. First you take this, you telescope the sum, appropriate to any partition you pick. You use the mean value theorem on any term to get that sum. And then you notice that the left-hand side actually doesn't depend on n. So you can take a limit of both sides, finally arriving at the definite integral on the one side and just that difference on the other side. So that's the fundamental theorem of calculus part 1.